Welcome everyone in this video lecture series on data structure. In today's lecture, we will discuss the concept of selection sort. To comprehend this algorithm properly, you should have basic understanding on sorting concept and the knowledge of bubble sort. I have already covered these two topics in my previous video lecture, and link for that video is given in the I button and also present in the description. You can think this selection sort algorithm as an optimization on bubble sort. So it is very important that you properly understand the bubble sort algorithm. So it is very important to check that video first and then continue this. Before going into details in the actual algorithm of the selection sort, we want to discuss the philosophy behind this selection sort process. The name selection sort is given because in this algorithm, we try to find out the maximum or minimum element present within the unsorted array. So we select that element and then we place that element in its correct position with the help of a swapping operation. That's why this name is given for this algorithm. You may relate this concept with the bubble sort, right? In the bubble sort algorithm, we also place the highest element in the last position in each iteration from my unsorted data. But in that case, we have to perform repetitive swapping operation. But in case of selection sort, we will process the entire unsorted data to figure out the position of the minimum element or maximum element based on your implementation. Then you have to place that element in its correct position. So in that case, only one swapping operation is required. So due to this reason, the actual time complexity of the algorithm will remain order of n squared. But the swapping count will get reduced significantly. Actually, the number of swapping required for this algorithm is bounded by order of n. So that means if I have n number of elements within my unsorted data, in that case, the worst case we have to perform n minus 1 number of swapping. Sometimes we may require less than n minus 1 number of swapping when a few elements already in their correct position. Fine. So now we will learn how to express this algorithm formally using algorithmic notation. So in this algorithm, I am considering that we have one array or list with name A, and it contains n number of elements. So here, this A is index addressable and index starts from 0. In the output, we will get one arrangement of A which is sorted in ascending order. And after that, the steps are given by which we can achieve this sorted order. So in this algorithm, I deliberately mark some segment of the algorithm with gray color. This section basically indicates the mean finding process. If we have one linear collection of data and if I want to find out which one is the minimum element, what do you have to do? We have to set minimum index to 0. Then we will search the remaining elements from 0 plus 1, that means from index 1 to the last index. So my last index will be n minus 1. If we get any element while processing which is less than the element present in the 0th index, so what we will do? We will update our mean index. So mean index is a variable which not holding the minimum element, rather it is holding the position of the minimum element. Okay. So when we will complete this iteration, within our mean index, we will have the minimum element within my array. Okay. So after that, what we can do, we can place that minimum element in the first position or index 0. So that will be the correct position for that element. So if we repeat this process again and again, and we shrink the size of the unsorted segment of the data, then what will happen? If we repeat this process n minus 1 times, it will place n minus 1 elements in their correct position, or I can say that nth element is also in its correct position. That's why this mean finding algorithm and the swapping code is placed within another iterative structure. The limit for this iterative structure will be from 0 to n minus times. So that means this code will run for n minus 1 times. So the limit is 0 to n minus 2, and number of iteration will be n minus 1, because it starts from 0 and ends at n minus 2. Clear? So this is the concept of selection sort. For better understanding, we will perform some dry run on a small set of data to understand the actual process of the selection sort. So let's say we have one array of integer with 6 elements. So here we show the first iteration of the outer for loop. So initially we will set the value of I equals to 0. So my inner for loop will run for j equals to 1 to j is equal to 5. So when j will become 6, we will stop the iteration within our inner for loop. So at the initial state, we will consider that mean index equals to the value of I. So initially, we will consider that the minimum element is present in the index 0. So now we will start our iteration. So iteration of inner for loop will start from j is equal to I plus 1. So that is j equals to 1. So in the index 1, we have the element 3, which is less than 7. 7 means the element present in the mean index, right? So that means my initial assumption is wrong. So I will update my assumption. So now I just store the value of j within my mean index variable. So now my mean index is 1. Then we will increment the value of j. So next time j will become 2. So this value is also, I want to say, the value present in the jth index is also less than the value present in the mean index. So what we have to do? We have to update the mean index variable. The mean index value was 1. So in the index 1, we have 3, and my current value pointed by j is 2. So we will update mean index to 2. So that means this is my current mean index. Then we will increment the value of j. Okay. So the value pointed by j is 5. So this element is greater than the value pointed by mean index. So no modification is required within my mean index variable. Next time we will increment the value of j, and it will become 4. In that index we have 1, which is less than 2. So we will update our mean index to 4. Then j will become 5. My mean index will remain the same. Then j will become 6. So this is the termination of the inner for loop. Then what we will do? We will swap the value between mean index and I. Okay. So value pointed by I is 7. Value pointed by mean index is 1. So we will swap their values. So after completion of the one iteration of the outer for loop, you can observe that the lowest element or the minimum element is placed in the index 0. So in the next iteration, what will happen? I will become 1 and the jth loop will start from I plus 1, that is from 2. So in that case, in that iteration, it will place the second highest element, that is the element 2 in the index 1. So if we repeat this process n minus 1 times, it will place all n elements in the correct position, in their correct position, and it will also ensure that nth element also in its correct position. So that's the concept of selection sort. The final outcome will remain the same as the bubble sort. Operating principle is very similar. In case of bubble sort, you can place the smallest element in its correct position also, in the first position also, right? But in that case, you have to perform several number of swapping. But in case of selection sort, in each iteration of the outer for loop, we have to perform only one swapping. And if my mean index and I are same, in that case, no swapping is required. Okay. Let's say in a particular iteration, a particular element is already in its correct position. So in that case, time, swapping is not required. So in the worst case, we have to perform n minus 1 number of swapping operation. So you can visualize the concept of selection sort in this animation. So here, green color is used to indicate the sorted segment of the array, and the sky blue is used to indicate the unsorted part. Okay, so here the red color is used to point out the current minimum value, and after the completion of that iteration, it will get swapped with the first unsorted element. Okay, so let me repeat this step again. So here you can see that all the elements are unsorted. So in that case, mean index is identified as 1, and then we perform the swapping. Now mean index is identified as 2. So it is already in its correct position. Next time, it will identify this 3 as the minimum, and then it will perform the swapping. Okay. So that means in the fifth iteration, it will place 5 in its correct position. All right. So now we will discuss the time complexity. So we have already considered that there exist two for loops. The outer for loop is indicated by I, and the inner for loop is indicated by J. In each iteration of the outer for loop, inner for loop will run for n minus I minus 1 time. So when the value of I is 0, it will perform n minus 1 number of comparisons. So when the value of I equals to 1, then it will perform n minus 2 number of comparisons. When the value of I equals to 2, it will perform n minus 3 number of comparisons. Sometime my I will become n minus 2, that is the limit for my outer for loop. In that case, it will perform 1 number of comparisons. So the total number of comparisons can be represented as n into n minus 1 by 2, right? Because we have the series 1 plus 2 plus 3 dot 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 up to n minus 1. So n into n plus 1 by 2 is the summation of the first n natural numbers. But in our case, the limit is n minus 1. So ultimately, this equation will become n into n minus 1 by 2. This is my cost polynomial, right? So this is nothing but a degree 2 polynomial. So we can say that number of comparisons is bounded by order of n square. So that is the worst case time complexity for my selection sort. Fine. Now, some FAQ regarding this algorithm. Is it a in-place sorting algorithm? Answer is yes. No auxiliary array is required, and sorting is done using constant extra spaces. Extra space is required, but that requirement is constant. Where extra space is required, we need one variable to store the mean index. We need variable to perform the loopings, but their requirement is constant. That is not dependent on my problem size. Fine. That's why we can say that selection sort algorithm is an in-place sorting algorithm. Is it a stable sort? Answer is no. We cannot give you the guarantee that it will maintain the property of the stable sort. For example, let's say we have three elements. Okay, 2, 2, 1. So I deliberately mark these identical elements with different color. Okay. So in the first iteration, what will happen? My mean index will point to the minimum element, that is 1. So this will be swapped with the first element. So this red 2 will get swapped with my 1. So that means in this case, we not able to preserve the relative order between identical elements. So that's why this is not a stable algorithm. Is early termination is possible in this algorithm? Unlike bubble sort, it is not possible to terminate this algorithm early if we able to sort the data. In case of bubble sort algorithm, we can keep track that how many whether any swapping happened or not within my data, right? So if for an entire execution of the inner for loop, no swapping happened, that means data is already sorted. And in that case, we can terminate the algorithm. But that kind of early termination is not possible in this selection sort algorithm. How many number of swapping is required? In the worst case, we have to perform n minus 1 number of swaps. So let's say the data is given in the sorted in reverse order. In that case, we have to perform n minus 1 number of swapping. In the best case, let's say my data is already sorted. So in such scenario, no swapping will happen. You should try to implement this code. The signature for the required functions are given here, and this will be same as the bubble sort. So here we need a separate function for the selection sort. So I just modify the bubble sort function with the help of selection sort. Other function will remain the same. I already explained the context of each of these functions in my previous video lecture, and I also explained why this V flag is required. If you follow that previous video, you can easily relate that concept with this selection sort algorithm. Okay, that's all in this video lecture. Thank you.